Alright, take 2, just gonna go over 8C and 8D. 8, 8C will be a very quick slide. So it's about using CAS technology which makes the calculation much quicker. Now, when you do it algebraically, do remember that to use the inverse function to find the definite integral if your function that you need to anti-differentiate is a little bit too tricky to solve by the technique that you know, using the idea that when you have a rectangle with a function, if you do the integral of the inverse function, they all add up together to form a rectangle. With the CAS, most of the time you will get an exact value. If not, then you end up with having just an approximate. You can also define an area function, so capital F in terms of x, and that will be your x variable, which is the upper boundary. And when you anti-differentiate, don't forget to change the variable name to t or u or anything else, as long as it's different from x. Alright, with 8D, what you're trying to do is find the volume of a solid of revolution. So you're going to start with a normal function, either in terms of x or y. And what you're trying to do is, the idea of revolution is you have a curve, you take that curve into a third dimension, you rotate it around an axis. So if I do this way, it's around the x-axis. If I do it around the y-axis, I will go that way. Okay? So the rotation about the x-axis will define the variable that we need to anti-differentiate, as well as the boundaries. So the boundaries will be in terms of x equals a to x equals b. Now you need to remember the formula. So you square your function. So y is a function in terms of x, you square it, and you have a pi factor. That is the formula that you need to use for a volume of revolution. If you rotate around the y-axis and you want to find the volume, it's in terms of y. The function this time needs to be a function of y. So if it's given in terms like y equals f of x, you need to do a little bit of the transposition and make x the subject, which is over here, x squared, and it's going to be a function in terms of y. Now your boundaries will be from y equals a to y equals b, and again you have a pi factor here. Let's go through a few examples. So you have a function square root of 4 minus x squared, which looks like a half circle. Okay, when you do a revolution, it gives you the volume of a sphere that will relate to the 4 pi on 3 times r cubed. To determine that volume, we're going to need to do a revolution around the x-axis. Your x, you start at x equals negative 2 to x equals 2. So integral is from negative 2 to 2. You have a pi factor here. You have your function in terms of x that you square. You get rid of the square root. You can take the pi outside the integral. The 4 minus x squared, you can anti-differentiate. It's just a polynomial. You substitute with the boundaries and you rearrange it. That gives you 32 pi over 3. Okay, and that's the visualization. So you start your function here, which is a half circle. When you do a full revolution, you need to imagine as a sphere or a ball. Next one, so you might not have a drawing. You have the function y equals x cubed. With part A, it's going to be a volume of revolution around the x-axis. So you use that as the function as it is. You have your boundaries. When you have now for part B, it's a volume of revolution about the y-axis. It does specify you the boundaries for y, but now that function is, you need to rearrange it and make x the subject. Volume of revolution, you have a pi factor. That's your y squared. You replace it in terms of function in terms of x. You anti-differentiate, and that gives you pi over 7. Here about the y-axis, so it's in terms of y. Your boundaries are y equals 0, y equals 1, and that's your x squared. That function x squared, so your x is actually x equals y to the power of 1 over 3. You square it, that gives you 2 over 3. You anti-differentiate, and you apply the boundaries, that gives you your volume as an exact value. Continue with the volume of revolution. Now, what if you have two curves, and what you're looking is you do a revolution of the interval between the two curves. What you end up is having a hollow shape. And to do that, what we do is we do the difference between the two volumes. So we do the volume of revolution of f to about the x-axis, the volume of revolution of g about the x-axis, and by doing the difference, the boundaries will be the same, so we can factorize that. That's the integral. And now your new function is fx squared, take away gx squared. Okay, so let's do a few examples. So the first one, you have actually two curves. You have 2e of 2x and y equals 1. So it's going to be from x equals 0 to x equals 1. So you can see those two curves. So that's my f and that's my g. So my f is my 2e of 2x and my g is y equals 1, or g of x equals 1. You apply the formulas. That's f of x squared, that's the g of x squared, which is still 1. You anti-differentiate, you substitute the boundaries, and that gives you your volume. Okay, just be mindful, it's always going to be positive. If you end up with a negative, it's possible you have confused or mismatched f and g. Another one, so you have f of x is 2x, which is above, g of x, which is an x squared, so it's between. You need to find the interval, so you make the two functions equal. That gives you an interval from 0 to 2. The corresponding y coordinates are 0 to 4. 0 and 4 could be useful if you're trying to find the volume of revolution around the y-axis. You will need the y coordinates. Here we're using the x coordinates, which is 0 and 2. So we apply the formula, that's x squared minus g of x squared. You substitute, that's a polynomial, easy to anti-differentiate. You use the boundaries 0 to 2. You substitute, you simplify your expression. Another one, so between it's not necessarily between two curves. With this one is about remember to use technique with circular functions. So because we square the function for a volume of revolution, we end up with, after taking the 9 out, we get a sine squared. Don't forget to remember to use your dual angle properties. So to lower the power from square to a linear, we're going to use the expression cos squared. And cos squared can be represented equal to an expression in terms of sine squared or cos squared, depending. So now by substituting, you have a half coefficient. You have a cos of double of 2x. So that's 4x. We can anti-differentiate and we get the value of the volume at the end. Okay. Last example, using again circular function, but this time is you will have to rearrange it. Your function is in terms of x. but it's asking you to find a volume of a revolution around the y-axis. So you need to anti-differentiate in terms of y. Your boundaries will have to be for y. So to find that, because you have x is from 0 to 1, you substitute into your function, you will find that it's going from 0 to pi, and that will be your boundaries for y. Here you need to make x the subject, so that gives you x equals sine of y over 2, and you substitute into your formula. So the formula is pi integral from y equals 0 to y equals pi for x squared in terms of dy. My x is sine of y over 2, you square it, that gives you that expression. You again use the cos of 2x in terms of sine of x, so that gives you that expression 1 minus cos of y over 2. We take the half out, we anti-differentiate, and we substitute the boundaries, and that gives you pi squared over 2. Alright, and that's the end of today's session on 8C and 8D. See ya.